Here we are at the base of Anderson Dam, and I'm here with Hemang Desai and Katherine Oven. Both work at the Water District, and we're going to talk about the dam here. So, Hemang, first, you're the project manager?
I'm the unit manager for the dam safety unit.
Okay, unit manager. And Katherine oversees capital projects?
Yes, I'm a deputy operating officer, and I have oversight on all the water utility capital projects at the district.
All right, so Hemang, can you tell me about Anderson Dam, the history, how did it come to be?
Yeah, before I do that, let me give you a brief background on all our reservoirs and dams. The district operates 12 reservoirs and 12 major dams, and most of these dams are under jurisdiction of Division of Safety of Dams and FERC, especially Anderson. Anderson is the unique one because it's also...
And what's FERC?
FERC is a Federal Energy Regulatory Commission.
Okay.
And most of our dams were built in the 1930s and the 1950s. Anderson Dam was built in the 1950s and is one of our major reservoirs because it contributes towards more than 50% of the local water supply. Its capacity is about 90,000 acre-feet, and it's connected to our creeks for water recharge. It's also connected to all our treatment plants and our water system.
So it's really our most important dam, an emergency water supply.
That's correct.
And you said there are 12 dams and reservoirs. I only think of 10. Are there two that I'm not thinking about?
Yes, there are two which are minor ones. We have the Coyote Perk Pond, which is a relatively small dam, but it's under DSOD jurisdiction. And then we have the Wasona Reservoir, which is also a fairly small reservoir, but it's under DSOD jurisdiction.
Okay, and talk about the how they built this dam back in the 50s.
Yeah, so as I said, the dam was built in 1950s, and it is what we call it's an earthen dam. What it means is it's predominantly built with rocks, soil, and clay. So the most important part of this dam is the clay core, which is in the middle of the dam. And it's pretty much entirely made up of clay. The whole purpose of that clay core is to prevent excessive water from seeping through the dam. And then to provide stability to the core, we have what are called shells on either side of the core, upstream side and the downstream side. These cores for Anderson are made from rockfill. These are the materials which were quarried from around here and basically dumped. So what we call it rockfill because it consists of very large rocks, as you can see on the surface here. And normally, it is very prudent to build these dams on competent foundation. What I mean by competent is bedrock. But in the 1950s, the technology, the know-how of how a dam would behave during an earthquake was not known. So a lot of this dam, especially the two shells, the ones I talked about, the downstream shell and the upstream shells, were built on less than desirable material. I mean, the downstream shell was built on lower final fill. What it is basically it was material derived from a local quarry here. During construction, it was just dumped. And it's definitely not a desirable material for foundation. On the upstream side, similarly, they left what is called alluvium. Alluvium is soil which is deposited with time on the bedrock, and again, it's fairly weak as compared to bedrock, and therefore, again, undesirable foundation material.
So, an earthen dam, just backing up a little bit, it's not like Hoover Dam, which is concrete. What's the difference between a concrete dam and an earthen dam?
It's the material of construction. The earthen dam is mostly built from earthen material, clay, rock fill.
Which is, why would we have earthen dams instead of concrete dams here?
That's a good question because earthen dams are more forgiving to movements. They're much more flexible, and they are also less expensive to build. So I think the choice of dam, of an earthen dam, was the right choice for what we have here. Earthquakes, things like that.
So you just mentioned earthquakes. So we know, because you said the foundation isn't ideal, and that's been discovered over the last few years. What is it that we're trying to do? Maybe Katherine, you can jump in. What is it we're trying to do with the project that we're undergoing?
So about 5 years ago, the district started a seismic stability evaluation study of each of the dams in the county that we own and operate. And we did a lot of investigation and testing using modeling techniques and the know-how of what we have learned as a society with regards to earthquakes and the devastating impacts of fault movement. Anderson Dam is located just a kilometer away from the Calaveras Fault, which is off to the hills over there. And a maximum credible earthquake was designed for what is the likelihood of what would be the maximum earthquake on the Calaveras Fault, and then
so the big one, basically.
The big one. And so then that was modeled with how would Anderson Dam and its existing embankments respond to that. And so what the study determined is that because of the finer fill, the alluvium, and the lower finer fill, as you call it, is located below this dam, that would have the capacity to completely liquefy. And you've heard the term liquefaction used a lot in terms of muds that are activated by earthquakes or the ground shaking, and they turn into jelly almost and become very unstable. So the seismic stability study determined that the top of the dam in a 7.2 maximum credible earthquake on the Calaveras Fault could slump up to 25 feet.
So you're saying that the top of the dam, about 200 feet from where we are, higher than we are, because about a 200-foot high dam, I think, could slump 25 feet, just would dip?
It would just dip right here at the crest down. And if the reservoir was full, that means that water would just start spilling over. That would, over time, a short time, would erode the entire embankment, and you could see a huge flood down in the valley from the reservoir spilling as a result of the earthquake.
So that's devastating. So what have we done to make sure that that doesn't happen, now that we know that that's the risk?
Yeah, so Katherine talked about the slumping. I mean, the dam crest would slump by about 25 feet. In addition, it would also crack severely. So, we estimated that the cracks would be another 20 feet deeper than the slump. So the total comes out to about 45 feet. And we have initiated a capital project to, address this issue in the long term. However, as an interim risk reduction measure, we have lowered the reservoir. What it means is we have kept it below this 45 feet mark until a project is constructed in order to keep the dam safe. Mm-hmm. So if there's an earthquake, it would slump and crack, but at least the water would be below that level and we wouldn't have any uncontrolled releases.
Okay, so by keeping the water low, folks don't really have to worry that this dam is going to fail, even if we had a major earthquake.
Correct.
Okay. But it has to be fixed.
Yes.
So go ahead and talk more about the project that we're going to build.
So we are underway with the beginning of the design phase of this project, and there are several different aspects to the project. So the embankment that we saw earlier, what we're going to have to do is peel away a certain portion of the embankment, off-haul all of the dirt that was piled up there 50, 60 years ago. And
so you're talking the embankment is this hillside that we're looking at right now?
That's correct.
So it's going to be carted off.
It's going to be carved away and carted off to a holding spot, and then we're going to replace it with stronger materials. All right, we're going to get additional materials from some of the quarries that were used back in 1950 to generate the rock fill that was used at the time. At the same time, once we peel back the layers of the embankment, we're going to peel it all the way back to bedrock. We're going to go in and excavate that alluvium and that lower fine fill, scrape it all clean so that we minimize the amount of liquefaction that may occur in the future. We're not going to get it all out, but we're going to get most of it out and then replace it with clean rock fill. So we're going to build the embankment back up to the level that it is today, but then we're going to add additional material. We call it a buttress. So it'll be additional rock fill material even on top of what's there today. In fact, where we're standing now is likely going to be covered by additional earthen dam buttress to really focus on maintaining the stability of the dam in future earthquakes.
So yeah, we're right at the toe of the dam right here. So how wide will this buttress go out?
So at this point, we're looking at about a 65-foot additional amount of space, an additional amount of footage that this buttress will go out. And that's on the upstream side as well as the downstream side where we're standing. All right. In addition, there's an outlet that was placed at the very bottom of the reservoir in the 1950s.
So that's a pipe that goes underneath the reservoir?
It's about a 4 or 5 foot diameter pipe that is used to release water from the reservoir. That in and of itself is also not a stably, it wasn't placed in a stable way. It was based on the technology that was known at the time, but we have to build a new outlet also as part of this project. So we're going to be tunneling through the abutment, we'll show that to you later, on one side of the dam, and we'll be putting in almost an 18-foot diameter tunnel that will house about a 4 to 5 foot diameter pipe.
And that sounds very similar to what we did at Lexington Reservoir a few years ago.
That's correct. That project was completed, I believe, in 2008. And for that reservoir, the outlet pipe kept collapsing over the years that it was in place. And so a tunnel option was deemed to be the best way to really allow the dam and the reservoir to function for the next 50 years. That's exactly what we're doing here. The dam is a little over 50 years old, and so we're putting the improvements in place so that it will serve as one of our key water supply reservoirs for the next 50 years, for the next generation.
So for that outlet, you're gonna tunnel through the hill.
That's correct.
Why is that better than just tunneling through the existing dam, or to replace the outlet to make is it because it's not stable to put it through the dam at all?
I think at this point, because the core of the dam that Hemang was referring to, I don't think we want to mess with that in terms of digging a bigger tunnel. We also want to have a tunnel that we can access manually so that we can maintain the pipe. Currently, the only way to maintain the pipe is to crawl through through the inside of the pipe. There is no other access to the pipe that's under the dam right now.
Do people do that? Do you have people crawling through that pipe?
Yes, we do inspect the pipe sometimes, and the way we do that is to send people from the downstream end into the pipe and have them crawl up.
How long is that pipe?
That pipe is about 1,200 feet long. That
doesn't sound fun.
It's not. I wouldn't do it.
Okay, so we've had earthquakes in the valley. We had Loma Prieta, wasn't on the Calaveras fault, right? But there've been earthquakes here. How has the dam performed?
The dam has performed satisfactorily over the years, in the sense that you're right, we have had a lot of earthquakes, a lot of seismic activities in this area in the last 50 years. 60 years to be more precise. And in the Loma Prieta earthquake, we did have some settlement of the crest. We did have some cracking, although it didn't compromise the safety of the dam. The design earthquakes we are talking about, which is required by, again, it's a jurisdictional dam, so it's required by DSOD and FERC to design the dam to the highest possible earthquakes, which is the maximum credible earthquakes. These earthquakes are probably a lot bigger than this dam has ever experienced.
Okay, so you're really planning for the worst. And what happens when there is a big earthquake here? How do you react? Do you have computers in the office that tell you whether a dam is having slumping issues, or how do you know what's going on with the dam after an earthquake?
So one of the components of the dam safety program is surveillance and monitoring. All our dams, including Anderson Dam, has numerous instruments which are installed within the dam, within the core, within the shells. These instruments, what they do is they monitor the water which seeps through the dam. What happens is once the water starts seeping through the dam, it applies pressure within the dam, or what we call as a piezometric pressure. Mm-hmm. And so we have instruments within the dam which monitor that pressure. What we look for on a very regular basis, all this data is basically transmitted to our laptops, through our automatic data acquisition system. And we analyze this data on a regular basis to see whether the dam is performing as intended. What I mean by that is that we know that there's going to be certain seepage, we know there will be certain pressure applied to the dam, but is it excessive or not? Okay. So in an earthquake, we would be monitoring these instruments to make sure that there is no detrimental effect of the earthquakes on the dam.
All right. Well, I think we should go to the top of the dam and take a look what it looks like from there.
Sure.
Okay. Okay, we're here at the top of Anderson Dam on the roadway that goes on the crest of the dam. And tell me again, in this maximum earthquake, what could happen where we're standing?
Well, in a maximum earthquake, if the dam has not been retrofitted, it would slump, it would settle or slump by 25 feet. And in addition to that, it might have cracks, which might go up to 40 feet deep.
So we might see big cracks in the road here, maybe along that would, you don't know, it could be like this way or...
Most of the dams would be transverse cracks, across the dam.
Okay.
And that's what we are worried about, because that would let the water from the reservoir out, through the dam.
And I see that the water level is low, and that's partly because it's been a really dry year, but it's also low because of the restrictions that we have on the dam, right?
Correct. The restriction is about 40 feet below the crest of the reservoir.
And how far below the crest is it right now?
It's at about, it's a little more than the restricted level. The restricted level translates to about 60% of the reservoir. Currently, the reservoir is at about 50%.
Okay, 50%. And we see some of the instruments you talked about. There's a little building here, looks like a little outhouse. What is that building for?
Yeah, that outhouse used to be the old control building for the old intake structure, which was replaced in the 1990s. The new control building is over there. Oh, okay. But we have used this, we have salvaged the building for the monitoring of the dam. What we do is basically we transmit all our data, which are collected from the instruments on the dam, if you can see them.
Yeah, they're all over. They're all over the face and both faces of the dam.
Correct. So all the data collected from those instruments are basically transmitted wirelessly to that building, and from there to our desktops.
Okay. So let's talk about the project more. Now we can see maybe some of the places where you'll be getting the fill to build up that buttress?
That's correct. From the crest here, right behind us, is a hill that we call Basalt Hill, and that was, you can see how it looks like it was carved out. It's now 60 years old, but we will be looking at that same site for additional rock fill.
So the dam fill that we're on, the dam was built by using rock from that hillside right there?
Yes, that's correct.
We're going to take from the same hillside?
Yes, yeah, just to strengthen the amount of rock that is in the embankment. And then straight behind us, right around the knobby area, right before the reservoir takes a sharp left turn, that's a formation of silica carbonate. It's very, very hard rock, and according to the history, at the time that they were building this dam in the 1950s, they could not blast that rock out. They couldn't use it, but we are also eyeing that as a potential source of really hard rock to use again to strengthen the embankment.
So how would we blast it? We have better ways of blasting it than they did back then?
Technology has changed, so that's the plan.
Bigger blasts, all right. So tell me about how, when this project is constructed, and how the water level is going to have to be really low, right?
Yes, especially for the construction of the upstream buttress. I mean, Katherine talked about the upstream buttress and the downstream buttress. We would have to lower the reservoir considerably, even dry it out. That would be accomplished by using a cofferdam. If you see, we pointed out at the silica carbonate knoll, and so the cofferdam would be located about there.
So you're going to build a cofferdam from these 2 points?
Correct, across those 2 points, and then pump the water out of this area so that we can build a buttress in the dry.
How tall is the cofferdam? Sounds like a big project in itself to build a cofferdam.
Correct. We just completed the planning phase, and it could be anywhere from 10 feet to 40 feet, but that number would be finalized in the design phase.
So there's going to be some water in the reservoir on the other side of that cofferdam, but it'll pretty much look like a puddle, or how will it look?
Yeah, it'll look like a puddle. How big that puddle is, that'll be decided, but it'll be considerably lower than what we have.
Yeah. And how long will it be that the dam will be kept that low, or the water level that low?
Most likely through the duration of construction of the upstream buttress, which could be anywhere from a year to a couple of years.
And when does it start?
It starts in 2016.
Okay, so 2016 to 2018 is when the construction will be happening?
Correct.
Okay, so that's the buttress. We got a buttress down here, and then the outlet, is it on this side?
Yes, the plan is to put the outlet through what we call the right abutment, and that would go on this side of that concrete structure that you see there is our emergency spillway. So the tunnel would go around that and then down through and exit out at the base of the dam where we were before.
And then empty into Coyote Creek?
Yes, we're going to reconfigure it so that it keeps the same portion of the creek wet that our current outlet is keeping wet downstream of the dam. There is, and I didn't mention this before, but there are trace faults. In addition to the Calaveras fault, there are other faults in this area, and there's a number of trace faults that run right underneath the dam itself. No one knows if those are active or not, but one reason for putting the pipe into a larger tunnel is to give the pipe room to move. So if there is a strong earthquake event and those trace faults below us rupture or move, that pipe can shift up to 4 feet horizontally or vertically and still stay intact.
How do you give that pipe the ability to move 4 feet? How does that? The pipe is pretty rigid, right?
It's rigid, but you add flexible joints in between the different pieces of pipe that will allow it to move.
Okay, that's interesting. And what about the spillway? Is that going to be modified at all?
Yes, the spillway is going to have to be modified as well. Because we're undertaking the seismic dam retrofit, the regulatory agencies that Hemang was referring to before, DSOD and the FERC, are requiring us also to revisit the protection that is needed in the event of what we call a biblical storm event. It's called a probable maximum flood, and it's based on really something that would happen once in 10,000 years, but that could come to pass where you would have a significant amount of rainfall in a short period of time. We're talking upwards of 20 inches over a 3-day period. The watershed would then release all of that runoff. The regulatory agencies want us to be able to pass the amount of water that would flow into this reservoir. Even if the reservoir was empty, it could not withstand that much runoff. And so we are actually going to be raising the sides of the spillway by 7 feet on each side. At the same time, the dam crest that we're standing on is also going to be raised by about 7 feet.
So in getting ready for this is a big project. It affects a lot of people. What have you done to reach out to the community to tell them about the project?
So we've had a few public meetings in the city of Morgan Hill that we've announced through newsletters and email invitations, and we've had very good turnout. So that was back in January of this year. We held such a public meeting to describe the planning phase, all the alternatives that we were seeking and evaluating. At this point, now that we're starting design, we're actually going to have another meeting in August next month. It's called the CEQA-NEPA scoping meeting. So as we start design, we're also going to be starting the analysis of environmental impacts by this project and developing the documentation for that. And so that also takes into account a series of public meetings that will be held to allow the community to express their concerns about potential impacts of the project, as well as to inform them what we have learned through our own biological surveys and the like. We've also met several times with the city of Morgan Hill. There is a homeowners association for the Holiday Lake Estates, which is a community that lives on the banks of the reservoir, kind of to our south here. And so we've met with them and described the project to them. We plan to continue talking to the community as much as we can in the course of design, and then especially once construction happens.
Okay. Well, how much does the project cost?
The total cost of the project right now stands at around $200 million. That includes the planning work, the design phase, and then the construction, which we right now are estimating will be about $150 to $160 million. And we'll refine that estimate as we get closer to the construction start date of 2016.
So before we let you go, Katherine and Hemang, this is the people behind your water. So wanted to hear just a little bit about what you like about your job. What is it, what keeps you going?
So I've been on my job here at the Water District for about 11 years, and I've always been at the management level for capital work. It's just a very satisfying and fulfilling job for me because I am part of the force that keeps water flowing into Santa Clara Valley and keeps civilization sustained as we know it. And that's really important for me to do for the next generation as well.
How about you, Hemang? What is it that you like about your job?
I think the most satisfying thing about my job is that I get to make sure that all the dams are safe. Mm-hmm. You know, the water supply is a very important part for a sustainable valley, but I think safety of the people is equally important, probably more important.
All right. Well, thank you, Hemang, and thank you, Katherine, who's gone off camera here, for coming out to Anderson Dam and telling us all about the project. And hopefully the community will stay involved and informed as this major project gets underway in the next couple of years.
Thank you.
Thank you.